6 of the Olympics. I'm sorry. I wasn't that good. You take it next semester.
Okay, so we're in the last section of this semester. Number 7, optimal dispatch of generation. So after this section, we finish the overview of the steady state analysis of a power system. So you'll be ready to take the next course, 422, on power system dynamic. Let's move on. Okay. So a little bit background of generation dispatch. If we consider a power system with multiple generators or multiple power plants in different types, some could be a hydro, some could be a fossil fuel. You can even have some renewable if they can be a dispatch. Different type of generation may have different fuel costs, especially for natural gas, nuclear, coal-fired power plants. So as the operator of the power system, you definitely want to minimize the cost of the entire power system. But to give you the room of dispatch, you want to have each power plant with capacity limit higher than their nominal output, right? And the total demand of system is less than the total generation of the entire system. So you will have some room to decide this power plant to generate more or less at this moment. Soon we need to solve a problem, right? We want to figure out optimal dispatch among all the generations. If your system has more spread out network, the transmission will also cause some transmission loss. You want to have generation in any time at any moment to be slightly higher than the total demand because you want to compensate the loss on the transmission. So that's also a part of consideration in such dispatch. Then we need to formulate a problem to minimize the total cost of the generation. And there are also some other formulations of similar problem which also consider the maximizing the benefit of reliability. So you want to minimize the cost and also maximize the reliability or stability of the system. So it can be a like multi-objective optimization problem or just single objective, depending on how you formulate the cost function. Okay, so you can treat just the fuel costs or the generation cost as part of the cost in your function. You want to minimize, or you want to formulate some benefit or price or the benefit or some income or whatever which you want to maximize as a negative cost. But anyway, so we need to formulate such a problem, and so all such problem is considered in the category problem called economic dispatch. And here we focus on real power generation. A broader type of problem of such a economic dispatch on real power generation is called optimal power flow. So power flow is basically you just solve the power flow. For each bus, you know the type. You know the type of the bus to be a slack bus, PV bus, PQ bus. So which means for each type, you gave two variables, either voltage magnitude angle, voltage magnitude and the power, IT power, or IT power and reactive power. So you gave two of the four variables at each bus. You solve the other two, and you create the same number of equations as the unknowns, right? So for each bus, based on the Kirchhoff current law, you create one equation, a complex equation that give you two real equations to solve the two real unknowns at each bus. And finally, you only find one solution. So that's power flow problem. But optimal power flow problem means you give each generation or power plant a little bit room. Instead of defining this generator need to generate active power P, you can give that P a certain range for P to vary. But you want to find out the minimal cost. So that's called the optimal power flow problem. So the economic dispatch problem just fall into that broader problem. And this optimal power flow problem actually fall into another more broader problem in mathematics, which is called nonlinear programming or NLP problem. So the nonlinear programming problem have two types, and we'll go through the simplest type. Then we gradually move to one type of nonlinear programming problem, which is very close to our economic dispatch problem. And meanwhile, we explain all the technique we need to solve such problem. So simplest one is just a optimization problem without any constraints. You just define the cost function and you just try any variable into the cost function to find out the minimal, really the smallest one in the range of the search. Then you can also add some constraints, which means those could be an equation. They need to hold all the time. So if you have one solution give you the minimal cost, but that solution doesn't meet those constraints, that's not a real solution. That's not a feasible solution. For instance, when you plug in the generation at different power plant, then you calculate the minimal cost based on their fuel cost. But when you try those generations in your power flow problem, it doesn't solve power flow. So which means even there could be a certain pattern you can dispatch generation in such a way, but they never make a power flow feasible. So the engineer or the operator, they don't know how to implement such solution. So they are not feasible solution. So you want to address those constraints in the equality tab. There could be also inequality tab, which means each power plant may have upper limit or lower limit. So those will be formulated as inequalities. This is a very brief background of generation dispatch. Let's start from a very simple unconstrained optimization problem. So here F is just a scalar function. We call it a cost function. Typically, if it really means a physical cost, it will be a positive value. If it means some benefit, it can be a negative value because negative cost will be can be considered as like some actual benefit. S1 to Sn can be the output, the active output of all the power plant. So we want to decide all the values. Before we talk about how to solve such problem, and we can start from very simple one-dimensional example. It's just a cubic function. Fs is equal a third of s cubed minus x. So if you want to find out the minimal value of this function, what is the minimal value of this function? What is the minimal value of this function? If s can take any number. Infinite, negative infinite, right? Because if you don't give it any constraint, it can be net infinite. Because, yeah, but if we narrow down a certain range, we can figure out maybe some locally minimal value. Let's try to draw the function. So here we want to just bound the range of s from maybe negative 1.5 to positive 1.5. Okay, if this is the case, it's very clear the minimal value of this function in that range. So that will be this point. Right, that will take a minimal value. So when x equals 1, when x equals 1, so this is really the maximum value. And they also have a maximal value which is this one, when s equals -1. So if you plug in, for instance, a positive 1 into the regional function, so that will be a third minus 1, so it will be negative 2/3. So that will be the minimal value, right? It will be negative 2/3. So that if 5 really means a cost of some benefit, this is the minimal value it can take. Yeah, so this is very simple for one-dimensional example. You just draw the function and you can visualize where the value can be the minimal. But if we don't want to draw this function, how do we solve, find the minimal or that local minimal or that local maximal in this range? One approach is we can calculate the first order derivative. So when you calculate first order derivative, original function will become this quadratic function. And if you let the this first order derivative to be 0, so that gives us 2 points, s equals -1 or 1, which means at those 2 points, the function is flat. So that's what the first order derivative equal to 0 mean. Okay, so locally at those 2 points, the function cost value doesn't increase or decrease, it just stay there. But definitely it can be maximum, it can be a minimum. But how do we differentiate that maximum from minimum? Because then we can we just investigate the slope near that point. So for instance, at the maximum point, the slope on the left-hand side is positive, on the right-hand side become negative. And at that point, the slope is exactly 0. So at the minimal point on the left is negative, on the right is positive, and here is 0. So this means at the minimal point, the slope gradually increase from negative to 0 and to the positive. And the maximal point, the slope decrease from positive to 0 to negative. Okay, so which means we can further calculate the second order derivative. And that second order derivative has to be positive, which indicate the slope is actually slope, which is the first order derivative itself need to increase. So then we calculate second order derivative. And if we want that one to be positive, 2s to be positive, so which means s has to be positive. So we have to find a point on the right-hand side of the y-axis where the slope becomes 0. Okay, so s equals 1 is the only local minimum in this area. So this is a very useful approach to find the minimal value or even the maximal value for any range of the x regarding a cost function. So we don't have to draw this figure at all. You just need to go through, calculate the second order derivative to make the value be 0 to find all the points with 0 slope, and then you further calculate second order derivative to find that point where the value is positive. So that point will be the local minimum points. Okay, then we can generalize this process to any functions with multiple x variables. The first step is we want to find the local minimum that satisfy 2 conditions. The surface one is a necessary condition is those minimum have to be a stationary point. Stationary point means it's flat locally. The slope in all directions has to be 0. The slopes in all directions are equal to 0 is formulated by this equation, which is the gradient vector. Gradient vector is a column vector. Each element is equal to the partial derivative of that cost function with respect to each x, which means in every direction, the slope has to be 0. If this equation holds, that point will be a stationary point. So this is a necessary condition to find the local minimum. The next condition is a sufficient condition. So we need to check a second order derivative. Then because they have a all combinations, because there are many variables, when you calculate the second order derivative, you can first calculate the first order derivative, and then for regarding one variable, then you move to the second variable. Then there will be if you investigate all the combination, they form a matrix, an n by n matrix. So such matrix is called the Hessian matrix. So the matrix has to be positive definite compared to the one-dimensional example with positive second order derivative. A matrix which is positive definite can be verified by checking all the eigenvalue. If all eigenvalue are positive, this matrix is positive definite. The matrix will have this form. It is just all combination of any partial second order partial derivative. Okay, so for instance, if you check the first row, the first variable will the one variable will be 1, and so the second variable will be starting from a 1 until n. So to categorize different columns. So if this f is smooth at this locally, so you actually can switch the order of either partial S1, Si or Sj. So it doesn't matter. The matrix will be asymmetric. This is the condition of a local minimum. So if you want to visualize what this local minimum look like, if you want to draw in the state space about all the variables, and based on you want to indicate the direction of the gradient, so which is like so at this point the f increase in all direction. So first stationary point means at this point is flat, or slope at in any direction will be 0. And if this point is local minimum point, which means the f will increase its value in all direction. Okay, so it's like a bottom of a valley. So the last step is you just check all the local minimum points to find which is really give you smallest f value. So that will be your final solution. Okay, so the procedure will be first you calculate the gradient vector which is a vector with all first order partial derivative. Second, you calculate the Hessian matrix, which is all combination of second order partial derivative, and that matrix has all eigenvalue to be positive. Then you find a number of solutions which are all local minimum points. So the smallest one will give you the final solution of the problem. If you only just find the local minimum, it doesn't give you a good solution, because for more complex curve, it's possible some local maximum may have a lower cost than some local minimum, right? Because in this case, if we want to investigate this area, this one definitely will be the final solution. Give you that's the local minimum point and with smallest cost. But if you didn't find this one, you miss this point, you only just check this local maximum and this local minimum, you may, if you don't compare the value, you can recognize this local minimum at the minimal, the global minimum, but which is actually even higher than another local maximum. So you have to make sure to find all stationary points without missing any one. Then the smallest one will be the final solution. Okay. All right, so now let's move to a second two-dimensional example, a cost function with two variables. This is very simple, right? Without solving this equation, if you want to find the minimal value of this function, x and y can take any value. So what is the minimal cost? If you try just plug in x and y by any number, what is really the minimal cost, minimal value of this function? So what does this function mean? In the X and Y in the plane, two-dimensional plane, so this one means the distance to the origin, right? So if you arbitrarily pick a point in the two-dimensional plane, so the distance from that point to the origin is minimized when you just stay right on the origin. Okay, so the minimal cost is simply just 0. Okay, let's try to solve this problem using our technique. We don't want to here when we solve this problem, we don't want to introduce too much geometric aspect, because if you're not very good at geometry, or even you're very good at geometry, but when we move to a high dimensional problem, it's impossible. You can visualize what does this like a 4-dimensional distance really mean. You want to find a reliable method to go step by step and finally to find a minimal solution, right? So when your operator to dispatch the thousands of generators, there's no way you can utilize any geometric method. So first we calculate the gradient vector. The gradient vector will be f partial x and partial s partial y. So basically partial f partial s will be basically 2s, and the second will be 2y. So you want this one be 0. If this one be 0, you can clearly tell there's only just a single stationary point, that is x equals 0, y equals 0. So that's just exactly the origin. So this problem only just have a single stationary point, and that is actually the final solution. But if you don't want to utilize any geometric ideas, you can definitely calculate the second order derivative. If you calculate second order derivative, you will tell actually it is positive definite matrix. I will show that later. So here, let's just visualize this gradient vector. So this gradient vector will change. It is a vector, will change the value or the direction or the length by plugging in different value. So if you plug in the value at 0, 0, which is the origin, this vector will become 0. So which is a 0 length vector without any direction. Okay. But if you move it a little bit, we will just plug in 1, 1. We just plug in 1, 1. And we draw, then this gradient vector will become 2, 2. 2, 2 means there's a little vector stay at that point, which is like in the directional field. So the length is, will be a triangle, right? So length will be 2 squared plus 2 squared and square root. So which will be a square root of 2. So this is the length. So that's why I draw this is the length. And the direction will be 45-degree angle, because both S and Y gradient will be positive. It's pointing to the 45-degree angle. This verified, if I arbitrarily pick a point at 1, 1, this point is definitely not stationary point, because that gradient vector is not 0 and also pointing to a direction. And the direction of the gradient vector indicate in which direction the cost function will increase. So if you move further to that direction, you will have a longer gradient vector. So cost function will be also bigger. And if you try along this circle as a radius of the radius will be a square root of 2. If you move along this circle in all directions, you will get different gradient vectors. But the green arrow will have the equal length, but they just pointing to a different direction. So that indicates if you move along this circle, the cost, the F value will increase when you move further from this circle. And if you move to that point, 2, 2, And you plug in here, the 2, 2 will become 2 by 2. 2 multiplied by 2 will be 4, 4, right? So this means you need to draw a longer vector, but it's still pointing to the same direction. So that verifies if you move away from the origin, the cost will increase. So it will increase in all directions. So finally, the only place the locally the gradient is become 0, it doesn't increase. The slope will be 0. It's only just origin point. Okay. So from this figure, we tell the necessary condition of the gradient vector being 0. It just, if we want to interpret that one in a geometric way, for this simple case, a 2-dimensional example. So each vector, the gradient vector, indicate the direction in which the cost can increase. In other words, they are moving away from the minimum point, from our solution. So we need to trace back based on the gradient vector to find in which direction that gradient vector can decrease until it becomes 0. So no matter which direction you try, you always converge to the same point, which is the origin which is the only stationary point of this function. So that is actually our final solution. Okay. All errors actually disappear at that point. If you verify and you calculate the Hessian matrix. So Hessian matrix, because the original cost function is only just quadratic function, when you calculate any second order derivative, it will become value. It's not function anymore. So basically, this is just diagonal matrix of 2, 2. It definitely is positive definite because it only have two eigenvalues which are equal. They're both 2. So this matrix is positive definite. So when we say a matrix to be positive, which really means it's positive definite. Okay, this verifies the only stationary point is also the minimum point, and that is the final solution. So that's pretty simple, huh? Okay. Yeah. So when you in the equation, when you see a matrix is bigger than 0, that equation means the matrix is positive definite. Okay. So it can have negative value, but all the eigenvalue are positive definite. So that's the definition of a positive matrix mean. Yeah, you can also, if you means like one matrix, you want to write this equation. This is literally speaking, that's the correct math. If you see this matrix is bigger or equal to 0, that means a semi-positive definite, which means the eigenvalue can be positive or 0. It cannot be negative. Okay, so if it doesn't matter any specific element to be positive or negative, because matrix means some transformation. Any matrix is a transformation of a diagonal matrix into a different direction. So you need to transform back diagonalize the matrix back to the diagonal matrix. So those eigenvalues really indicate what this matrix truly is before the transformation. We'll talk about that like a positive definite, negative definite, or indefinite later. You buy another more complex example. But for this simple case, f has only just one local minimum point at 0. That's our origin. Okay, let's move to a more complex case. It's not like quadratic anymore. It's just a nonlinear function. Even I don't know what the physical meaning of this function is, but just let's try using the ideas from the previous example to see how we can find the global minimum point of this function in certain area. Okay, let's assume we narrow down a certain range, which is basically this area. So that the surface in blue just indicate how the cost function can change in x or y in 2 directions. You see the surface completely curved, right? There's some area it can have like the valley, which is at the center, at the origin. So when x and y are both 0, so that actually give you the minimal value. So from from the geometry, so if x and y are both 0, so what is the function value? So cosine 0 will be 1, so be -2 squared, right? -4. So the minimal value will be here. That's the bottom of this valley at origin. Any other point will be higher than this one. But that's not the only local, may not be the only local minimum points of this function if you draw the surface in a bigger area. But let's narrow down this area. So there will be a different type of stationary points. And the type of stationary point can be categorized based on the gradient vector. If we expect the gradient vector in near any stationary point, right? Because if the gradient vector all pointing to different direction at that point, so this must be minimal point. If all the gradient vector converge to this point, that's a maximal point. If some direction is leaving, some direction is coming back, so that's called a saddle point. So on the bottom surface, that arrows actually indicate all the gradient vectors. So based on the length, you can tell. So this origin will be 0. So because all the arrows will vanish at that point. But there are also some other area you can see the arrow becomes smaller, and finally become a dot. So for instance, those 4 corners. And another is those points. So there are 9 points where all the arrow vanish. So you see here it has the longest arrow, right? So it will increase in this direction and decrease and to this point. So what happened on the surface is it starts from the local minimum and first increase the cost and eventually decrease the cost, increase the cost, and finally the slope go back to 0. So this one will become a maximal point that corresponding to this projection. And definitely the 4 corners all about the same type. It's just a locally maximal point. And there are also a point which is like this one. So in this direction, it will increase, but in the other direction, outside direction will decrease. So that's saddle point. It's like the saddle surface. Okay, so we can color those 3 types of stationary point by orange, green, and blue. The orange means really the minimum point. The green means the maximal point, and blue means saddle point. So we have 1 minimum point and 4 maximal point. So if I draw all of them, so this is another maximal point, and 4 stationary saddle point. Okay. So you see, if you only just check the necessary condition, you just calculate the first order derivative, apply to this cost function, you will have a 9 stationary points. Okay. But if you further check the sufficient condition for the local minimum by calculating the Hessian matrix, only for the center, the origin, which will give you a positive definite H. Because in all direction is increase, it will increase, so which indicate a positive eigenvalue for that at that point. And then for the green region, which are actually the maximal points, so their Hessian matrix will be negative, which means a negative definite. All eigenvalue will be negative. And for the blue, the point centered at each blue circle, and that point is called saddle point. So in one direction, the the gradient vector decrease, the other direction, the gradient vector will increase. So if you check the Hessian matrix for all eigenvalues, some eigenvalue will be positive, some eigenvalue will be negative. Okay, so by checking the both, finding the stationary point and then verify the whether the Hessian matrix to be a positive definite, you'll be able to find the true local minimum points. That's still not the final solution. If you have multiple local minimum points, you need to compare the values, the F value at all such points to find really the smallest one. Okay, so let's summarize the approach to find the global minimum. We want to find really just one solution. Or if you have multiple solutions, they will all have exactly same the cost, and which are smaller than any other points. So in theory, we need to take three steps. The first step is we calculate the gradient vector, make the vector be 0, we can find those stationary points, including minimum, maximum, and saddle points. That's not enough. And the next step is we check the Hessian matrix to make sure the Hessian matrix to be positive definite. That will cross off some of those stationary points. And finally, we narrow down to the local minimum points. And to find really the global minimum, we have to compare F value at those local minimum points and to find the smallest one. So that one will give you the minimal generation cost. That will be the solution of a dispatch problem. But in practice, if the problem doesn't have many maximum saddle points, we can skip step number 2, which means you just go ahead to find all the stationary points, and then you jump over to step 3. Then you compare F value at all stationary points to find which one is smallest one. This in practice is good if you don't have many candidate solutions. If you have so many candidate solutions, you want to add step 2 to narrow down your calculation for the cost function to those only minimum points. Okay, so this actually conclude the approach for the minimization or optimization problem without any constraints. If we have to deal with optimization problem with constraints, we need to first transform the problem into an unconstrained optimization problem. So how do we do that? So next, we just add one equation, or maybe a k equations. So each equation is actually a equality constraints. It can be a power flow equation in our problem. Because I want to do a generation dispatch, so the cost function just simply tell you if you plug in the generation values, and this tell you how much fuel cost you have. But in order to deliver those generation, the electricity generated by the power plant through the network, you also need to make sure the network can have a power flow solution. So that will be the equality constraints. If you solutions or any candidate can meet the equality constraints, we call such candidate as a feasible solution. The feasible solution, which means they don't give you the minimal cost, but they are not bad. They don't violate any reliability, okay? Because they can give you the feasible power flow patterns or conditions you can operate your system, but although it doesn't give you the minimal cost, okay? Because reliability is definitely more important than economic factors of your system. They're feasible, but it's not the most economical solution. So the approach to convert this constraint optimization to an unconstrained optimization is a technique which is called Lagrangian function. So we have a regional cost function, but we introduce another cost function, more general cost function called Lagrangian. Lagrangian is actually based on the original cost function. So we use L. So the L is a function of all the variables like generations. And also we introduce some new variables. So the new variable, the physical meaning of each new variable is the price you want to pay to violate any constraint. Okay, so if you problem have no constraints, you don't need there's no constraint to be violated. So there's no price to pay. Don't worry, you can arbitrarily pick any S value and just determine which is the really local minimum. But once I give you some constraints, could be powerful equation. If you violate this equation, you're going to pay some price. So that price is also some variable to be determined because there could be some solution. You need to pay higher price, but the overall cost can be smaller, right? There could be another solution. You pay lower price, but the overall cost is bigger. So I just gave you the room. You can decide how you want to dispatch generation, and also you're okay to pay some price. So the lambda here, it just added additional k variables, each defining the price, violating those constraints. So this new cost function will be like a linear combination of the original cost function and the total cost, total price you're going to pay for violating those constraints. And the lambda has another meaning, it's just called the Lagrange multipliers from lambda 1 to lambda k. So k will be the number of constraints you have. Okay. Okay, so starting from now, we can find the stationary point of this new cost function, and then we can compare which one gave us the minimal cost. So that will be the final solution of our problem. So let's try finding the stationary point of this Lagrangian function, the new cost function, L. Stationary points will have the gradient vector be 0. So now the gradient vector is not about the original cost, it's about this new function, L. Because it has two type variables, so there will be a two type of gradient element. The first type is just simply partial L but partial X, any variable. Because this is a linear combination, so we'll have two items. The first one is just partial F, partial X. The second item will be just the first order derivative with respect to that X for all the sum of the prices of violation, and which is equal to a linear combination of each equality constraints with respect to that X, and this one has to be 0. And the second type of elements in the gradient vector will be partial L, partial by partial lambda, each lambda. So if you do that, that's actually exactly equality constraints. So equality constraint appears as second type of element in your gradient vector. So it means by introducing this new cost function, we didn't forget about those equality constraints. We keep them as part of the gradient vector. And if we really expect the gradient vector to be 0, then those equality constraints need to hold. Okay. All right, so this is the most important step. So next one, we just go ahead to solve those equations, and when we find all the station points, we can jump over the step number 2. If you don't want to really calculate the Hessian matrix to solve the eigenvalue, you just find a station point about L. And they're all 0. And then you just jump over to the step number 3 to check all the values of X, plug into back to the cost function to find which is really the true minimal one. Okay. Probably I will leave this example to Wednesday.